Chapter 8 of A Popular History of Astronomy During the 19th Century. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. A Popular History of Astronomy During the 19th Century by Agnes Mary Clerke. Part 2, Chapter 8, Planets and Satellites Continued, Part 4. The satellite theory has derived unlooked-for support from photometric inquiries. Professor Seligler pointed out in 1888 that the unvarying brilliancy of the outer rings under all angles of illumination from 0 degrees to 30 degrees can be explained from no other point of view. Nor does the constitution of the obscure inner ring offer any difficulty, for it is doubtless formed of similar small bodies to those aggregated in the lucid members of the system, only much more thinly strewn, and reflecting consequently much less light. It is not, indeed, at first easy to see why these sparser flights should show as a dense dark shading on the body of Saturn. Yet this is invariably the case. The objection has been urged by Professor Hastings of Baltimore. The brightest parts of these appendages, he remarked, are more lustrous than the globe they encircle. But if the inner ring consists of identical materials, possessing presumably an equal reflective capacity, the mere fact of their scanty distribution would not cause them to show as dark against the same globe. Professor Ziegler, however, replied that the darkening is due to the never-ending swarms of their separate shadows transiting the planet's disk. Sunlight is not, indeed, wholly excluded. Many rays come and go between the open ranks of the meteorites, for the dusky ring is transparent. The planet it encloses shows through it, as if veiled with a strip of crepe. A beautiful illustration of its quality in this respect was derived by Professor Barnard from an eclipse of Japetus, November 1, 1889. The eighth moon remained steadily visible during its passage through the shadow of the inner ring, but with a progressive loss of luster in approaching its bright neighbor. There was no breach of continuity. The satellite met no gap corresponding to that between the dusky ring and the body of Saturn, through which it could shine with undiminished light, but was slowly lost sight of as it plunged into deeper and deeper gloom. The important facts were thus established, that the brilliant and obscure rings merge into each other, and that the latter thins out towards the Saturnian globe. The meteoric constitution of these appendages was beautifully demonstrated in 1895 by Professor Keeler, then director of the Allegheny Observatory, Pittsburgh. From spectrographs taken with the slit adjusted to coincidence with the equatorial plane of the system, he determined the comparative radial velocities of its different parts, and these supply a crucial test of Clerk-Maxwell's theory. For if the rings were solid, the swiftest rates of rotation should be at their outer edges, corresponding to wider circles described in the same period; while if they are pulverulent, the inverse relation must hold good. This proved to be actually the case. The motion slowed off outward in agreement with a diminishing speed of particles traveling freely, each in its own orbit. Keeler's result was promptly confirmed by Campbell, as well as by Deslandres and Bélopolsky. A question of singular interest, and one which cannot refrain from putting to ourselves, is whether we see in the rings of Saturn a finished structure, destined to play a permanent part in the economy of the system, or whether they represent merely a stage in the process of development out of the chaotic state in which it is impossible to doubt that the materials of all planets were originally merged. Mr. Otto Struve attempted to give a definite answer to this important query. A study of earlier and later records of observations disclosed to him in 1851 an apparent progressive approach of the inner edge of the bright ring to the planet. The rate of approach he estimated at about 57 English miles a year, or 11,000 miles during the 194 years elapsed since the time of Huygens. Were it to continue, a collapse of the system must be far advanced within 3 centuries. But was the change real or illusory? A plausible but deceptive inference from insecure data. Mr. Struve resolved to put it to the test. A set of elaborately careful micrometrical measures of the dimensions of Saturn's rings, executed by himself at Pulkowa in autumn of 1851, was provided as a standard of future comparison, and he was enabled to renew them under closely similar circumstances in 1882. But the expected diminution of the space between Saturn's globe and his rings had not taken place. A slight extension in the width of the system, both outward and inward, was indeed hinted at, and it is worth notice that just such a separation of the rings was indicated by Clerk-Maxwell's theory, so that there is an a priori likelihood of its being in progress. Yet Hall's measures in 1884 through 1887 failed to supply evidence of alteration with time, and Barnard's, executed at Lick in 1894 through 1895, showed no sensible divergence from them. Hence much weight cannot be laid upon Huygens' drawings and descriptions, which had been held to prove conclusively a partial filling up since 1657 of the interval between the ring and the planet. The rings of Saturn replace, in Professor G.H. Darwin's view, an abortive satellite scattered by tidal action into annular form, for they lie closer to the planet than is consistent with the integrity of a revolving body of reasonable bulk. The limit of possible existence for such a mass was fixed by Roche of Montpellier in 1848 at 2.44 mean radii of its primary, while the outer edge of the ring system is distant 2.38 radii of Saturn from his center. The virtual discovery of its pulverulent condition dates then, according to Professor Darwin, from 1848. He conjectures that the appendage will eventually disappear, partly through the dispersal of its constituent particles inward, and their subsidence upon the planet's surface, partly by their dispersal outward, to a region beyond Roche's limit, where coalescence might proceed unhindered by the strain of unequal attractions. One modest satellite revolving inside Mimas would then be all that was left of the singular appurtenances we now contemplate with admiration. There seems reason to admit that Kirkwood's law of commensurability has had some effect in bringing about the present distribution of the matter composing them. Here the influential bodies are Saturn's moons, while the divisions and boundaries of the rings represent the spaces where their disturbing action conspires to eliminate revolving particles. Kirkwood, in fact, showed in 1867 that a body circulating in the chasm between the bright rings, known as Cassini's division, would have a period nearly commensurable with those of 4 out of the 8 moons, and Meyer of Geneva subsequently calculated all such combinations, with the result of bringing out coincidences between regions of maximum perturbation and the limiting and dividing lines of the system. This is in itself a strong confirmation of the view that the rings are made up of independently revolving small bodies. On December 7, 1876, Professor Asaph Hall discovered at Washington a bright equatorial spot on Saturn, which he followed and measured through above 60 rotations, each performed in 10 hours, 14 minutes, 24 seconds. This, he was careful to add, represented the period, not necessarily of the planet, but only of the individual spot. The only previous determination of Saturn's axial movement, setting aside some insecure estimates by Schroeter, was Herschel's in 1794, giving a period of 10 hours 16 minutes. The substantial accuracy of Hall's result was verified by Mr. Denning in 1891. In May and June of that year, 10 vague, bright markings near the equator were watched by Mr. Stanley Williams, who derived from them a rotation period only 2 seconds shorter than that determined at Washington. Nevertheless, similarly placed spots gave in 1892 and 1893 notably quicker rates, so that the task of timing the general drift of the Saturnian surface by the displacements of such objects is hampered to an indefinite extent by their individual proper motions. Saturn's outermost satellite, Japetus, is markedly variable, so variable that it sends us, when brightest, just 4½ times as much light as when faintest. Moreover, its fluctuations depend upon its orbital position in such a way as to make it a conspicuous telescopic object when west, a scarcely discernible one when east of the planet. Herschel's inference of a partially obscured globe turning always the same face towards its primary seems the only admissible one, and is confirmed by Pickering's measurements of the varying intensity of its light. He remarked further that the dusky and brilliant hemispheres must be so posited as to divide the disk viewed from Saturn into nearly equal parts, so that this Saturnian moon, even when full, appears very imperfectly illuminated over 1/2 of its surface. Zollner estimated the albedo of Saturn at 0.51, Müller at 0.88, a value impossibly high, considering that the spectrum includes no vestige of original emissions. Closely similar to that of Jupiter, it shows the distinctive dark line in the red, wavelength 618, which we may call the red star line, and Janssen, from the summit of Etna in 1867, found traces in it of aqueous absorption. The light from the ring appears to be pure reflected sunshine, unmodified by original atmospheric action. Uranus, when favorably situated, can easily be seen with the naked eye as a star between the 5th and 6th magnitudes. There is indeed some reason to suppose that he had been detected as a wandering orb by savage watchers of the skies in the Pacific long before he swam into Herschel's ken. Nevertheless, inquiries into his physical habitudes are still in an early stage. They are exceedingly difficult of execution, even with the best and largest modern telescopes, and their results remain clouded with uncertainty. It will be remembered that Uranus presents the unusual spectacle of a system of satellites travelling nearly at right angles to the plane of the ecliptic. The existence of this anomaly gives a special interest to investigations of his axial movement, which might be presumed, from the analogy of the other planets, to be executed in the same tilted plane. Yet this is far from being certainly the case. Mr. Buffum in 1870 1872 caught traces of bright markings on the Uranian disk, doubtfully suggesting a rotation in about 12 hours in a plane not coincident with that in which his satellites circulate. Dusky bands resembling those of Jupiter, but very faint, were barely perceptible to Professor Young at Princeton in 1883, yet though almost necessarily inferred to be equatorial, they made a considerable angle with the trend of the satellite's orbits. More distinctly by the brothers Henry, with the aid of their fine refractor, 2 gray parallel rulings separated by a brilliant zone were discerned every clear night at Paris from January to June 1884. What were taken to be the polar regions appeared comparatively dusky. The direction of the equatorial rulings, for so we may safely call them, made an angle of 40 degrees with the satellite's line of travel. Similar observations were made at Nice by Messrs. Perrotin and Tholen, March to June 1884, a lucid spot near the equator in addition, indicating rotation in a period of about 10 hours. The discrepancy was, however, considerably reduced by Perrotin's study of the planet in 1889 with the new 30-inch equatorial. The dark bands thus viewed to better advantage than in 1884 appeared to deviate no more than 10% from the satellite's orbit plane. No definitive results, on the other hand, were derived by Professors Holden, Schaeberle, and Keeler from their observations of Uranus in 1889 through 1890 with the potent instrument on Mount Hamilton. Shadings, it is true, were almost always, though faintly, seen, but they appeared under an anomalous, possibly an illusory aspect. They consisted not of parallel, but of forked bands. Measurements of the little sea-green disk, which represents to us the massive bulk of Uranus, by Young, Schiaparelli, Safarik, H.C. Wilson, and Perrotin, prove it to be quite distinctly bulged. The compression at once caught Barnard's trained eye in 1894, when he undertook at Lick a micrometrical investigation of the system, and he was surprised to perceive that the major axis of the elliptical surface made an angle of about 28 degrees with the line of travel pursued by the satellites. Nothing more can be learned on this curious subject for some years, since the pole of the planet is now just turned nearly towards the earth, but Barnard's conclusion is unlikely to be seriously modified. He fixed the mean diameter of Uranus at 34,900 miles, but this estimate was materially reduced through Dr. C's elimination of irradiative effects by means of daylight measures executed at Washington in 1901. The visual spectrum of this planet was first examined by Father Secchi in 1869, and later, with more advantages for accuracy, by Huggins, Vogel, and Keeler. It is a very remarkable one. In lieu of the reflected Fraunhofer lines, imperceptible, perhaps through feebleness of light, 6 broad bands of original absorption appear, one corresponding to the blue-green ray of hydrogen, another to the red star line of Jupiter and Saturn, the rest as yet unidentified. The hydrogen band seems much too strong and diffuse to be the mere echo of a solar line, and might accordingly be held to imply the presence of free hydrogen in the Uranian atmosphere. This, however, would be difficult of reconcilement with Keeler's identification of an absorption group in the yellow with telluric water band. Notwithstanding its high albedo, 0.62, according to Zollner, proof is wanting that any of the light of Uranus is inherent. Mr. Albert Taylor announced, indeed, in 1889, his detection, with Common's giant reflector, of bright flutings in its spectrum, but Professor Keeler's examination proved them to be merely contrast effects. Sir William and Lady Huggins, moreover, obtained about the same time a photograph purely solar in character. The spectrum it represented was crossed by numerous Fraunhofer lines and by no others. It was then presumably composed entirely of reflected light. Judging from the indications of an almost evanescent spectrum, Neptune, as regards physical condition, is the twin of Uranus, as Saturn of Jupiter. Of the circumstances of his rotation we are as good as completely ignorant. Mr. Maxwell Hall, indeed, noticed at Jamaica in November and December 1883 certain rhythmical fluctuations of brightness, suggesting revolution on an axis in slightly less than 8 hours. But Professor Pickering reduces the supposed variability to an amount altogether too small for certain perception, and Dr. G. Merle denies its existence in toto. It is true their observations were not precisely contemporaneous with those of Mr. Hall, who believes the partial obscurations recorded by himself to have been of a passing kind, and to have suddenly ceased after a fortnight of prevalence. Their less conspicuous renewal was visible to him in November 1884, confirming a rotation period of 7.92 hours. It was ascertained at first by indirect means that the orbit of Neptune's satellite is inclined about 20 degrees to his equator. Mr. Marth having drawn attention to the rapid shifting of its plane of motion, Mr. Tisserand and Professor Newcomb independently published the conclusion that such shifting necessarily results from Neptune's ellipsoidal shape. The movement is of the kind exemplified, although with inverted relations, in the precession of the equinoxes. The pole of the satellite, owing to the pull of Neptune's equatorial protuberance, describes a circle around the pole of his equator in a retrograde direction, and in a period of over 500 years. The amount of compression indicated for the primary body is at the outside 1/85th, whence it can be inferred that Neptune possesses a lower rotary velocity than the other giant planets. Direct verification of the trend theoretically inferred for the satellite's movement was obtained by Dr. C in 1899. The Washington 26-inch refractor disclosed to him, under exceptionally favorable conditions, a set of equatorial belts on the disk of Neptune, and they took just the direction prescribed by theory. Their objective reality cannot be doubted, although Barnard was unable, either with the Lick or the Yerkes telescope, to detect any definitive markings on this planet. Its diameter was found by him to be 32,900 miles. The possibility that Neptune may not be the most remote body circling round the sun has been contemplated ever since he has been known to exist. Within the last few years, the position at a given epoch of a planet far beyond his orbital verge has been approximately fixed by two separate investigators. Professor George Forbes of Edinburgh adopted in 1880 a novel plan of search for unknown members of the solar system, the first idea of which was thrown out by Mr. Flammarion in November 1879. It depends upon the movements of comets. It is well known that those of moderately short periods are, for a reason already explained, connected with the larger planets in such a way that the cometary aphelia fall near some planetary orbit. Jupiter claims a large retinue of such partial dependents. Neptune owns 6, and there are two considerable groups, the farthest distances of which from the sun lie respectively near 100 and 300 times that of the earth. At each of these vast intervals, one involving a period of 1,000, the other of 5,000 years, Professor Forbes maintains that an unseen planet circulates. He even computed elements for the nearer of the two, and fixed its place on the celestial sphere. But the photographic searches made for it by Dr. Roberts at Crowborough and by Mr. Wilson at Daramona proved unavailing. Undeterred by Deichmüller's discouraging opinion that cometary orbits extending beyond the recognized bounds of the solar system are too imperfectly known to serve as the basis of trustworthy conclusions, the Edinburgh professor returned to the attack in 1901. He now sought to prove that the lost comet of 1556 actually returned in 1844. But with the elements so transformed by ultra-Neptunian perturbations as to have escaped immediate identification. If so, the wanted planet has just entered the sign Libra, and being larger than Jupiter, should be possible to find. Almost simultaneously with Forbes, Professor Todd set about groping for the same object by the help of a totally different set of indications. Adams' approved method commended itself to him, but the hypothetical divagations of Neptune having scarcely yet had time to develop, he was thrown back upon the residual errors of Uranus. They gave him a virtually identical situation for the new planet with that derived from the clustering of cometary aphelia. Yet its assigned distance was little more than half that of the nearer of Professor Forbes' remote pair, and it completed a revolution in 375 instead of 1,000 years. The agreement in them between the positions determined, on separate grounds, for the ultra-Neptunian traveler was merely an odd coincidence, nor can we be certain until it is seen that we have really got into touch with it. End of section 29.